So we talked about the real underlying meaning of the determinant. Okay, it's in some sense it's a measure of the change in area under the transformation. So you can think of it as like maybe a ratio between the new area and the old area. Okay, I'd like to put this into practice a little bit though, and I'd like to do it by taking a look at a couple of our transformations that we've seen previously. Okay, let's take as a first example rotation of 180 degrees. We saw that that brings the x coordinate to minus x and the y coordinate to minus y. Okay, we can write that in terms of our transformation matrix M by taking the coefficients of the a, b, c, d. But because it's much more simple than this, there's, for example, x goes to minus x, there's no y component. So you can write this directly as m is minus 1 for the coefficient here and 0 for y. And y is 0 for the x and minus 1 for the y. So this is the transformation matrix of a 180 degree rotation. Okay? So we want to find out what is the determinant of this matrix. What is the determinant of this matrix? Well, we can write it like this. Minus 1, 0, 0, minus 1. With two straight lines. That means the determinant of that matrix. Well, it's AD minus BC. So AD is minus 1 times minus 1 minus BC is 0 times 0, which is equal to 1 minus 0, which is 1. So the change in area under a rotation, well, it's been scaled by 1, meaning it's unchanged. But we would expect as much. We would expect as much. Because if you think about it, pen's not working. If you think about it, if you take an area, okay, and you rotate that area around here, to say, to that position there, the area does not change. You're just doing a rotation. You're not scaling anything. You're not changing the size of anything. You're just moving things. You're rotating it. Okay? So it gives you a really intuitive idea for why the determinant of this rotation matrix is 1. Okay? Let's take a look at another matrix. There's the scaling transformation. Okay, that takes x to k times x and y to k times y. So you're scaling either up or down. The transformation matrix for this would be k, 0, 0, k. Okay, just taking the coefficients and putting them into the transformation matrix. Well, the determinant of this is a times d, k times k, minus 0 times 0, which is k squared. Okay, which makes sense. If you scale, if you have an area here and you scale x and y by the same amount, okay, the area is going to be related to the scaling factor, and because it's an area we're talking about, it's k squared. Okay, so it makes intuitive sense. Okay, good. That should be there. All right. Let's think about an arbitrary rotation. Let's think about an arbitrary rotation. So we have r theta, okay, and the matrix for this rotation is like this. This is an active rotation, moving the point from one position to another. Okay, rotating the point from one position to another. The determinant of this matrix is a times d minus sine theta times sine theta. Which is equal to cosine squared theta plus sine squared theta, which is equal to 1. Again, any rotation, doesn't matter if it's 180 degrees or 90 degrees or 1000 degrees or anything, 4.7. It can never change the area. It's just a rotation. Okay. The last thing I want to say is that the determinant is, while it is some kind of measure of area, it can also be negative. Okay. Let's take reflection transformation in the x-axis. This has the matrix transformation matrix 0, 1, 1, 0, 0, minus 1. Okay, if we take the determinant of this, it's 1 times minus 1 minus 0 times 0, which is equal to minus 1. So the area hasn't changed, it hasn't altered the area, it's reflected well, it's a reflection transformation, so it doesn't alter area, it doesn't do any scaling. Okay, but it has changed the sign. Okay, so you can think of the determinant as not just some measure of the change in area, but also as having a kind of an orientation. Okay, it has a signed value, it can be positive or negative. So if you reflect, right, if you reflect some shape in the x-axis, for example, okay, it goes from having a positive area to a negative area. So just be wary of that. The determinant can be both positive and negative.